Can people walk through walls? According to the theory of quantum mechanics, the answer is yes. Then why can't you? Perhaps your luck isn't good enough. You might have heard of the quantum tunneling effect. It always occurs on a microscopic scale. Is there such a possibility on a macroscopic scale, like with our human bodies? For instance, could you suddenly find yourself on Mars, or even at the edge of the universe while walking down the street? Some might say it's possible, but the probability is extremely small, almost zero. However, almost zero is not zero. How small is it exactly? Today, I'll simplify all the conditions and calculate the probability of a human body tunneling, just to put your mind at ease. At the end of the 17th century, Newton proposed the law of universal gravitation, and from then on, mathematics began to demonstrate its powerful dominance over the real world. The movements of the sun, moon, and stars became predictable, and the existence of Neptune was successfully predicted. By the early 20th century, Einstein first explained time dilation and length contraction through the theory of special relativity, revealing that mass and energy are essentially equivalent. He then used the field equations of general relativity to describe the curvature of spacetime, predicting phenomena such as the bending of starlight, gravitational redshift, gravitational waves, and the existence of black holes. Every great physical law is often accompanied by a mathematical formula. Through these formulas, we can explain known phenomena and predict things beyond our current understanding. Years later, people verified these predictions and found them to be true. Thus, some say that mathematics is a tool for physicists, a language to describe nature. However, from various indications, it seems to be more than just a tool. It appears to be a fundamental law of nature itself. This feeling becomes even stronger when you understand quantum mechanics. After Schrodinger formulated the Schrodinger equation, Max Born quickly provided the Born interpretation, stating that the square of the absolute value of the wave function represents the probability of a particle appearing at a certain point in space. The Schrodinger equation essentially states that kinetic energy plus potential energy equals total energy. Here, potential energy includes electric potential energy, gravitational potential energy, and other combined potentials. For a particle free from any external forces, its potential energy is zero. Substituting this into the Schrodinger equation, the square of the absolute value of the wave function is a constant, meaning that a completely free particle has an equal probability of appearing anywhere in space. It is everywhere. Of course, this is an ideal scenario. The real world is always full of constraints. Let's consider a real-world example, such as an electron orbiting a hydrogen nucleus. For the electron, its potential energy mainly comes from the electric potential energy provided by the nucleus. The further out the electron is, the greater its electric potential energy. The potential energy field outside the nucleus is like a thick wall of potential energy, with the potential inside the wall higher than the total energy of the electron. We generally call this a potential barrier. Intuitively, without absorbing external photons, the electron can never cross the potential barrier to escape from the nucleus, as this would require its kinetic energy to be less than zero during the escape process, which is clearly impossible. This is similar to how a satellite can never overcome gravitational potential energy to escape Earth without active acceleration. However, never try to understand the microscopic world using macroscopic laws. Everything must be based on actual calculations. When we substitute the particle's potential energy into the Schrodinger equation, a miracle happens. To simplify the calculation, We directly represent the potential barrier as a wall. When the wave function encounters the potential barrier, it splits into two waves. One is reflected back by the wall, and the other passes through the wall after attenuation. Of course, the amplitude of the wave that passes through the wall is much smaller than that of the reflected wave. This means that the probability of finding the particle on the right side is certainly smaller than on the left side, indicating that the probability of tunneling is not very high. However, please note that this probability is not zero. Quantum mechanics allows a particle to pass through a wall with potential energy greater than its total energy. How is this possible? If mathematics were merely a tool used by physicists, the real world would have no obligation to adhere to the solutions of these equations. In 1927, less than a year after the Schrodinger equation was published, several physicists, including Friedrich Hund, obtained this tunneling solution. However, since people at the time did not see any practical physical significance in it, they chose to ignore it. It wasn't until 1928 that George Gamow, a 24-year-old Russian-American physicist, also noticed this solution. Gamow, who later became one of the proposers of the Big Bang theory, believed that this tunneling solution had real physical significance because it could explain nuclear decay. We know that atomic nuclei are composed of protons and neutrons, held together by the strongest of the four fundamental interactions, the strong nuclear force. Given the strength of this force, why do some atomic nuclei sometimes release particles and decay? Through a series of calculations, Gamow found that the actual decay probability of atomic nuclei perfectly matched the tunneling probability derived from the equation. In other words, the microscopic world can indeed tunnel through walls. This phenomenon became known as the quantum tunneling effect or quantum tunneling. Other physicists, upon hearing about quantum tunneling, began to study it extensively. This research revealed that quantum tunneling is virtually everywhere, such as in nuclear fusion. Nuclear fusion is the process of combining two small atomic nuclei to form a larger one, releasing a tremendous amount of energy in the process. The reason the sun shines and emits heat is not because it burns coal, but because it continuously undergoes a vast number of nuclear fusion reactions. However, a problem arises. We know that atomic nuclei are positively charged. Like charges repel, so the closer two nuclei get, the greater the repulsive force they experience. Only when they cross a certain critical distance do they enter the realm of the strong nuclear force and become firmly bound together. But the key is that they must be able to cross this distance, which requires the nuclei to have extremely high kinetic energy. In the macroscopic world, the kinetic energy of microscopic particles translates to temperature. The core temperature of the Sun is approximately 15 to 25 million degrees Celsius. Even accounting for pressure and other factors, this is still far from the temperature required for actual hydrogen nuclear fusion. It is precisely because of quantum tunneling that nuclear fusion occurs in the Sun's core at temperatures that are not excessively high. In other words, we owe our ability to enjoy the Sun's light and heat to quantum tunneling. Additionally, quantum tunneling is ubiquitous in the field of biology. Plants can perform photosynthesis, enzymes can accelerate biochemical reactions, and genetic material can self-repair. All of these processes rely on quantum tunneling. You might have also heard of the scanning tunneling microscope in your high school physics class, which is said to be able to visualize the arrangement of atoms. In fact, it is not an optical instrument like a conventional microscope. Instead, it displays the probability of electrons undergoing quantum tunneling on the surface of atoms. The specific principle is that when a probe approaches a metal surface, there is a very tiny gap between the probe and the surface. This gap acts as a thin potential energy wall. Electrons on the metal surface, which would normally be unable to overcome this gap to escape the nucleus, can now potentially tunnel through this gap to reach the probe due to the quantum tunneling effect. As a result, the probe detects a current. The varying heights of atoms create different distances between the probe and the surface, akin to walls of different thicknesses. Different wall thicknesses correspond to different tunneling probabilities. Thus, the scanning tunneling microscope can precisely reconstruct the atomic arrangement on the metal surface based on these probabilities. The mathematical description of the quantum tunneling effect provides us with a tool to understand this phenomenon. Returning to the question posed at the beginning of the video, what is the probability of a human body tunneling to Mars? The formula for tunneling probability is This formula not only explains the theoretical foundation of quantum tunneling, but also enables us to make precise measurements using scanning tunneling microscopes. Through this formula, we can calculate the probability of tunneling under different conditions, thereby gaining a better understanding of the fascinating phenomena in the microscopic world. Suppose we want to calculate the quantum tunneling probability of a person traveling to Mars. First, we treat the person as a large particle and set the parameters as follows. Mass of the person, m equals 70 kilograms. Thickness of the potential barrier, L equals 2.25 times 10 to the power of 11 meters, the distance from Earth to Mars. The height of the potential barrier V-E can be approximated as the gravitational potential energy required to overcome Earth's gravity, given by mgr, where r equals 6.371 times 10 to the power of 6 meters, Earth's radius. It can be seen that this value is so small that it can be considered zero. Although it is theoretically possible to calculate the quantum tunneling probability of a person traveling to Mars, the actual probability is extremely small, practically zero. Quantum tunneling is not applicable on a macroscopic scale, primarily due to the limitations of decoherence and mass effects. Therefore, the idea of humans tunneling to Mars through quantum effects is impossible in reality. Compared to the age of the universe, this probability is almost negligible. Thus, while the quantum world is full of fascinating possibilities, in the macroscopic world, we still need to rely on science and technology to achieve the dream of interstellar travel.